Hi everyone, my name is Kamalawasan. I am a computer science PhD student at University of Warwick. Today I am going to talk about our research paper titled as High Throughput Multidimensional Tridiagonal System Solvers on FPGAs. This is a joint work with my supervisor Gihan Mudalihe from University of Warwick and with other collaborators Isfan Reguli from PPCU Hungary and Suhaib Fahmy from KAUST, Saudi Arabia. The aim of this work is to study feasibility of FPGAs as an alternative accelerator platform for multidimensional tridimensional system solver applications and, if feasible, finding the optimal design techniques for the FPGAs and evaluating the performance of FPGAs against commonly used GPU accelerator devices. Many scientific and HPC applications involve solving partial differential equations numerically. Popular domains are computational finance, computational fluid dynamics. Solution methods like ADI, multigrid utilize tridimensional system solvers. We can solve this 2D heat diffusion equation using ADI method. It breaks these time steps into two and solve multiple tridimensional system like this along HDIM and YDIM. As tridimensional solvers are popular in HPC, previous works have developed tridimensional solver libraries for GPUs and CPUs. In recent years, there is an increasing need for energy efficient architectures as well as low latency processing, for example, in financial computing. Let's look at the FPGA accelerator platform, which is usually preferred for low power and low latency computing. FPGAs provides circuit elements that can be connected to build circuit for an application. This is the block diagram for the Silent U280 FPGA card. It consists of data circuit elements such as lookup tables, a data signal processing block, and block memories, and as well as the routing fabric to connect these elements. Large silence FPGAs are divided into SLR regions, and user must be aware of the slow connection speed between these SLR regions. And modern FPGAs comes with high bandwidth memory. In contrast to CPUs and GPUs, FPGAs doesn't come up with fixed architecture that can be exploited by instructions. Instead, user can create custom architecture for particular application and can control memory hierarchy and data movement. For example, if user want to read along the set lines, it is efficient to read H lines and put the H set plane onto on-chip memory because elements along H lines are contiguous. From the on-chip memory, user can read the set lines. Here, on-chip memory acts as a cache. Pipeline data flow graph-based computation is possible on FPGAs and irregular parallelism can be achieved. Data circuit can be scaled into multiple compute units working in parallel to get superior performance on FPGAs. Yet, challenge in using FPGA is programming overhead. Recent HLS tools drastically reduce development time compared to hardware description language-based designs, but HLS also require customization and skills on data flow programming model. Let's look at the characteristic of our application class we are interested. The tridiagonal system that we are going to solve is in this format. Here A or AU equal to D. Here A is this tridiagonal matrix with bandwidth 1 and U is the unknown we have to find and D is the right hand side. Solution method for this kind of system is well known and popular solvers are Thomas, PCR or parallel cyclic reduction and Spike. Common application cases like ADA scheme solves multiple tridiagonal systems. Here, ADA solves multiple systems along each dimension, usually iteratively. This requires re-evaluation of those algorithms due to the natural parallelism offered when solving multiple independent systems. Applications usually consist of many kernels. Let's look at the high-level execution of kernels in GPU and FPGA. GPU's input and output comes from and to global memory, and GPU's global memory usually limiting factor for the performance for many applications as well as ADA applications. Attempt to fuse or pipeline or unroll iterative loop of kernels for the better data reuse on GPU will require global memory synchronization points. This would lead to performance degradation. In contrast, FPGAs focus on kernel-to-kernel communication, and it focuses on internal data radios. This helps to do optimization like fusing, pipelining, unrolling iterative loop on FPGA easier, and to get better effective memory bandwidth even with lower global memory bandwidth. Detailed information on current state of art is available on paper. However, to our knowledge, the best library available to compare is Silis PCR library, and we are going to compare our library solution with it. Let's look at the contribution of this work. In contrast to previous works, we theoretically evaluate tridiagonal system solvers for FPGAs, presenting design and optimization strategy based on problem size, dimensionality, number of systems, and data flow paths. Develop new batch tridiagonal solver library based on Thomas and Tile Thomas solvers along with data path components for multidimensional system solves. Compute units implemented using this library can be scalable using HBM. We also present analytical performance model to aid design space exploration and to check profitability of FPGA design. We note that models were over 85% accurate when comparing with actual runtime. We implement two non-trivial applications using new library on Silis U280 FPGA. Same applications were optimally implemented using state-of-art GPU library on NVIDIA V100. We see competitive performance and over 30% of energy saving on FPGA for most complex application in its largest configuration. Okay, we have seen motivation and introduction. We have also seen contribution of this work. Next, we are going to see popular tridiagonal system solvers along with theoretical comparison and optimization when targeting FPGAs. Then about multidimensional tridiagonal solvers, its characteristic and procured optimization for data access. Then we will see tiled tridiagonal solvers for larger systems. After that, we will be briefly looking at performance models. Thereafter, we will see detailed performance comparison with applications we implemented using our library with implementation on NVIDIA V100. Finally, lessons learned and conclusion. Let's look at the popular tridiagonal system solver algorithm. This is the Thomas algorithm and this is PCR algorithm. Thomas algorithm has two loops and each loop do n iteration approximately, making it on complex algorithm. And we can see there is a dependency between iterations of loops, and there's a dependency between loops also, like second loop has to wait completion of the first loop. For the PCR one, outer loop does log n iterations and inner loop does n iteration, making it n log n complex algorithm. And we can see there is no dependency within the inner loop iterations. Hence, this loop can be partitioned and parallelly executed in many co-architectures. Let's look at the challenges posed by Thomas solver for FPGA implementation. Challenge one is inter-iteration loop dependency. Iteration latency for forward and backward loop, LF and LB, are in tens of clocks due to floating point arithmetics. Due to iteration dependency, next iteration can't be executed in pipeline before completion of current iteration. Circuits for these loops can be better utilized by solving group of system in interleaved manner. Here, group size G should be higher than arithmetic pipeline latency. FPGA on-chip memory can be utilized for interleaving systems. Second challenge is circuit for forward loop and backward loop can't operate in parallel. When batch size is large, system can be put into multiple groups. In that case, forward solve and backward solve can process different groups Gn and Gn-1 respectively. Parallel execution of forward and backward loop on FPGA will require ping-pong or double buffer-based data movement. Calculated latency for Thomas solver with batch size B and system size N is as here in this expression. Similarly, we can calculate latency for the PCR solver with inner loop unrolled F2 times to improve the performance, and latency is given by this expression. Here L is the arithmetic pipeline latency. We can see that if B is large, PCR latency is log n over F2 times higher than Thomas solver latency. And even PCR with FU1 requires more DSP resource than the Thomas solver. Hence, the Thomas is the efficient algorithm considering the fixed amount of FPGA resources. Here, we are going to see how optimized Thomas solver can be implemented. As we mentioned previously, systems need to be interleaved and it will require additional loop if systems comes from sequentially from 5 These 3 loops can be implemented as 3 hardware modules on FPGA, and all 3 modules will work in parallel. Algorithm 3 outlines the structure of forward solve module, which takes input from 5 and push outputs to another 5 Here, ping pong buffer is used for the continuous execution of this forward solve, and all 3 loops will execute in parallel using this ping pong buffer based technique. We have seen multidimensional ADA application solves equation along each dimensions. Since there are many systems to be solved, we can batch them and apply optimization we have seen previously. For example, solving along HDM, there will be y into z numbers of systems. Data layout of mesh points is also important. In a data layout where H is contiguous, solving YDIM and StatDIM will require threaded memory access. For those cases, we can read HY plane and HZ plane, and we can put that into on-chip memory and then read Y lines and Z lines to improve the memory access. In order to improve the performance, we will need multiple Thomas solvers operating in parallel as vectorized units. These solvers require inputs from different systems. Wider memory ports are preferred as it gives better memory bandwidth. Let's assume we use forward wide memory port. When reading along YDIM, each forwards will correspond to different systems that can be directly fed into Thomas solvers. In contrast, when reading along HDIM, all 4 words will correspond to the same system. In that case, we read 4 H lines into on-chip memory and then read 4x4 block, and then we do transpose, and then we feed it to Thomas solvers. Similar transpose optimization is required on GPU as well. We have seen that we have to interleave group of systems to use arithmetic pipeline effectively for Thomas solvers on FPGAs. This would require huge on-chip memory for larger system. Tiled Thomas solver algorithm gives solution for this. It breaks system into tiles. Here we break into 2 tiles, and modified Thomas solver algorithm can be applied on these 2 tiles. After forward sweep and backward sweep of Thomas algorithm, we will get this system. Here, values in the red can be used to form reduced system, and reduced system can be solved by Thomas or PCR algorithm. Once we have solution for the reduced system, we can substitute that values and find the solution for the full system. We have implemented Thomas and Thomas PCR variant of this tiled algorithm on FPGA. The main components that adds latency in this class of applications are ping pong buffers and window buffers if stencil loops are also integrated. Algorithm 4 describes the simple ping pong buffer based implementation. We can see there's a block difference between input and output points. Hence, the delay in the ping pong buffer is 1 block or like m elements in this case. Other than that, looping through the mesh point is the main contributor of the latency. Looping through latency depends on the loop initiation interval, which depends on the how effectively we pipeline the loops on FPGA. Let's look at the use cases of latency model. Latency models can be used to predict performance. It can be used with resource estimation model to find optimum design parameters. In this way, we can check profitability of implementing a design on FPGA compared to other architectures. Models can also be used when designing, determine the minimal FIFO buffer size in branches like this. Also, when we are making decisions to fuse kernels or duplicate computation or choosing an algorithm like tiled Thomas algorithm or standard Thomas algorithm. We have developed models for each application and we have tested them and it gave over 85% accuracy. Let's move to the experimental evaluation. System specification of our experiment is given in this table. Here we use Silence Alveo U280 FPGA card and NVIDIA Tesla V100 for the GPU comparison. And FPGA comes with HBM memory with maximum bandwidth of 460 gigabytes per second, and GPU's global memory bandwidth is 900 gigabytes per second. First, we will see the performance comparison of our library with Silence PCR library. We compare for the batch cases from 1 to 1000 size, and we compare the system size 128 and 1024. For the 1024, we are using tiled Thomas algorithm. We can see that for the smaller batch size, Silence FPGAs, Silence PCR is relatively better than our library, but for the larger batch size, our library performs over 1 magnitude better than the Silence PCR library for both 128 and for the 1024 case as well. And we can see that unrolling the inner loop of the Thomas PCR only marginally improved the performance, but it consumed more resources. Let's look at the performance evaluation of two non-trivial representative applications. First one is ADA heat equation. We evaluate for 2D, 3D cases using FE32 as well as FE64 arithmetics. We also implement tiled ADA using FE32 arithmetic. Other application is stochastic local volatility. It is from financial computing and uses FE64 arithmetics. FPGA kernels were implemented using C++ for Vivado. Same applications were implemented using state-of-art GPU library, which is this Tridiagonal library, and it is implemented using CUDA C++. We tried CPass to solve Tridiagonal system, but Tridiagonal gave better or similar performance when solving along dimensions, and it natively support multidimensional meshes without data layout transformation. We chose NVIDIA V100 as fair but challenging competitor because of close fabrication technology as well as comparable bandwidth. Let's look at our first application, 3D ADA heat diffusion application. It consists of 4 main steps in an iterative loop. First step calculates the RHS mesh and coefficient meshes, and other steps solve tridiagonal systems along different dimensions. On GPU, this accumulation step is fused with Tridiagonal subteam, and on FPGA, this accumulation step is fused with RHS calculation step. On FPGA, all first 3 steps can be pipelined and parallelly executed. 4th steps can't be pipelined because it would require whole mesh to be stored on chip memory. These first 3 steps and decoupled set module will operate on meshes in a ping-pong manner for parallel execution. This implementation will require several transformations similar to 2D case, which we are going to see in the next slide. This diagram shows the main component for FPGA 2D ADA implementation. We use separate data structure for accumulation for the data flow programming model. After reading from HBM, several optimizations are applied, such as rows to 8x8 blocks, 8x8 transpose, and call to row transpose. Since all the modules are pipelined in the 2D case, iterative loop can be unrolled, but this would require a delay buffer, which can be implemented using HBM by enforcing memory operation at particular distances. Unrolling the iterative loop will increase the latency, but pipeline can be better utilized by larger batch sizes. Moreover, multiple compute units like this can be instantiated based on availability of FPGM and FPGA HBM ports and resources. Let's look at the runtime comparison of FPGA implementation and GPU implementation for ADA applications. Here we do for different batch sizes, and for the 2D ADA case and for the single precision, we can see the FPGA performs better than the GPU, and for double precision case also we can see FPGA performs better. We attribute like parallel Thomas solvers and unrolling the iterative loop and multiple compute units for better performance on FPGA. We can also see that FPGA runtime prediction closely matches with the actual runtime. And for the 3D ADA case, here also we can see both single precision and double precision FPGA performs better than the GPU implementation. Here also we have multiple Thomas solvers working in parallel, as well as there are multiple compute units, and we have mentioned like in 3D ADA we can't unroll iterative loop. Here also like we can see that predictions are very closely matching with the actual runtime. Let's compare achieved bandwidth and energy consumption of ADA application on FPGA as well as GPU. Here we note that we report effective bandwidth, and we are going to compare the bandwidths for largest mesh configuration with largest bed size. And first, we are going to compare 2D ADA application using single precision. FPGA reaches around 620 gigabytes per second, even though its maximum HBM bandwidth is 460 gigabytes per second. This is because of unrolling and pipelining modules. GPU reaches a good 418 and 554 gigabytes per second bandwidth along X and Y dimensions. And here we note that GPU's maximum theoretical bandwidth is 900 gigabytes per second. And when it comes to energy, FPGA saves over 80% of energy consumed by GPU. And for the 2D ADA double precision case, FPGA reaches around 422 gigabytes per second, and GPU's bandwidth was higher around 441, but then later it slightly dropped to 281. And but YSOL bandwidth remains in a good level, and it goes up to 548 gigabytes per second. When it comes to energy, FPGA saves 76.4% of energy consumed by GPU. For the 3D ADA single precision case, FPGA reaches around 358 gigabytes per second bandwidth. Here we note that we are not unrolling iterative loop. That's why there's a slight drop from 620 to 358, because we can't unroll iterative loop for the 3D application. GPU maintains good level of bandwidth around 400 gigabytes per second, and for the set-sol it reaches 563 gigabytes per second. And when it comes to energy, FPGA saves over 73.1% of energy consumed by GPU. And for the 3D applications double precision case, FPGA's bandwidth slightly dropped to 276 gigabytes per second, because here we only have 3 compute units, and GPU's H bandwidth was higher, but for the largest configuration it dropped to 338 gigabytes per second. But Y and Z bandwidth remains in a good level, 436 and 565. When it comes to energy consumption, FPGA saves 65.2% of energy consumed by GPU. Let's compare the performance of tiled ADA heat diffusion application on FPGA as well as GPU. First, we are going to compare for the Thomas PCR variant. In that one, FPGA performs better for the smaller batch sizes, and for the larger batch sizes, FPGA gives competitive performance with GPU. And when it comes to the model predictions, it closely matches with the actual runtime. Thomas variant also gives the similar performance as the Thomas PCR variant on FPGA. And this table describes the bandwidth and energy consumption of the FPGA and GPU implementation. This is for the Thomas PCR implementation. Thomas implementation also gave similar results. And here, for the largest configuration, FPGA's bandwidth reaches around 222 gigabytes per second. This is slightly lower than the other values we have seen. This is because we can't pipeline X and Y salts because of the larger mesh. We only can pipeline RHS and HDIMM salt. A GPU reached a good bandwidth, but for the largest configuration, it dropped to 342 gigabytes per second. But YSOL bandwidth remains high, and it reaches around 560 62 gigabytes per second. When it comes to energy, FPGA saves over 50% of energy consumed by GPU. Let's look at our second application, stochastic local volatility. It is a 2D financial computing application using a double precision arithmetic. It implements Hansdorfer-Weber scheme, again an ADE method. It has 9 kernels inside an backward iterative loop, and this HP-pred kernels does high order stencil operation, and HP matrix kernel calculate tridiagonal matrix coefficient. We duplicate and fuse the HP matrices computation in HP-preds to save the on-chip memory in data flow graph-based computing. And right solve X and right solve Y solves the tridiagonal system along X and Y dimensions. Since this application consists of many loops along with many data structures, make this application close to production workload found in the industry. Let's compare the performance of SLV application on FPGA and GPU. We have two mesh configuration, 40 into 20 and 100 into 50. And we do batch sizes 30, 300, and 3000. When comparing the runtime for the smaller mesh, FPGA gives good performance for the smaller batch sizes, and for the larger batch size, FPGA gives competitive performance with GPU. And FPGA's runtime prediction closely matches with the actual runtime. When it comes to a larger mesh, FPGA gives competitive performance for the smaller batch sizes, and for the larger batch size, GPU gives a good performance. And runtime prediction is closely matching with actual runtimes. When it comes to bandwidth and energy consumption for the smaller mesh, FPGA reaches around 281 gigabytes per second, and GPU's H-solve bandwidth remains low, around 123 gigabytes per second, but Y-solve reaches a good bandwidth of 327 0.65 gigabytes per second. And when it comes to energy, FPGA saves over 47.2% of energy consumed by GPU. And when it comes to bandwidth and energy consumption of the larger mesh, FPGA reaches around 318.36 gigabytes per second, and GPU's X and Y solves also reach a good bandwidth of 421 gigabytes per second and 429 gigabytes per second. And when it comes to energy, FPGA saves over 28.0% of energy consumed by GPU. Let's look at the lessons learned through this work. When Thomas Solver is optimally implemented on FPGA for batched computation, it is the most efficient algorithm for medium-sized meshes. Custom data path, on-chip memory, and register-based transformation gives current throughput, but transformation using GPU's cache doesn't always give intended throughput. Example, block transpose for GPU. Pipelining kernels on GPU is challenging due to global memory sync points, but FPGA kernels can be easily pipelined. This makes FPGAs is competitive even with global memory bandwidth. Finally, modern FPGAs with HBM memory can challenge GPUs even for the bandwidth-bound applications and could provide energy-efficient computing. In conclusion, in this work, we have developed a new tridiagonal solver library for solving multidimensional tridiagonal system. Several loop optimization and transformations were applied on the library modules. We also implemented tridiagonal solver library for larger systems, along with data flow techniques and custom modules for full system design. We re-evaluated popular tridiagonal solver algorithm for batch systems using models. Further, our theoretical models achieved over 85% of accuracy for test cases we have done. New library also outperformed silence PCR as predicted by the models for batched implementation. We validated new library and models by implementing two non-trivial applications on silence Alveo U280 FPGA. We also compared the performance with NVIDIA V100 using state-of-art GPU library. We see better or competitive performance on FPGA and over 30% of energy saving for most complex applications, larger configuration. Library can be found in this GitHub repo, and it is publicly available. We invite you to try and give us feedback. We are grateful for our funding bodies and to the organization and people those provided resources and advisors. For more details of this work, please read our paper. Thank you so much for listening.